where can you pursue astronomy in India, and this is useful for you. Even if you're doing a PhD in some other topic, it will be useful to help for you when students ask you questions. So I'm giving you information for you to kind of tell other people as well in your college. Uh, other parts of being, other ways of doing being an astronomer. Okay, so this is so sorry about the timer in front. There's some screw up with the display because I have Mac. Now this is taken from the vision document prepared for the Principal Scientific Advisor's office. Here you see gamma rays, X-ray, UV, visible, infrared, submillimeter, and radio, and these are pictures of all the telescopes India has in them. Okay, so let's go from the beginning. Radio, we have the telescope at Ooty. How many of you been to Ooty for holidays, for vacation? And how many of you not seen the telescope and come back? All of you. Okay. So next time you go there, you know what to do. Then there's a GMRT in near Pune, and then there's a Gauribidnot in Karnataka, which also, how many of you seen? How many of you know there is a telescope in Karnataka at Gauribidnot which operates in the radio? You. Okay. Then India does not have any telescope in the submillimeter. There is one waveband in which India does not have any telescope at all, sadly, and people are trying to fix that, including Mahesha sitting here. In visible infrared, we have a host of telescopes across India, and I'll show them and I'll show you what they are. In the ultraviolet, we have what's the difference between this and this? This one here and this one here. Just visually, it's a spacecraft. This is on ground. Why do you have to go to space? Did somebody talk to you yesterday about it? Turbulence for ultraviolet. But why do you have to put a ultraviolet telescope in space? Atmosphere blocks it, right? Ozone primarily blocks it. What happens if it wasn't true? Astronomers will be very happy if you can see ultraviolet from the ground. It's cheaper for us to build telescopes. But what happens if that happens? What happens to us if you can see UV from the ground? Skin cancer, right? Skin cancer, cheap astronomy telescopes. I think the balance is fairly clear. So we have a telescope in space called AstroSat. I'll tell you a little bit about it, which observes from ultraviolet up to hard X-ray, right? And then in gamma rays, we have gamma. Now, what about radio? Why is radio on the ground and not in space? Because the atmosphere is transparent to radio. Up to how many megahertz is it transparent? How low can you go in frequency in the radio and still be transparent? Do you hear FM? Do you hear Bangalore FM in Mysore? No. Do you hear Bombay FM in Mysore? No. But do you hear Bombay shortwave radio in Mysore? Why? But why? Why do you hear shortwave radio from Moscow and Paris and London, but not FM from Bangalore? I'm still talking just physics. I haven't got to astronomy yet. Okay, so I want the answer. I want the answer at lunch, after lunchtime. Okay, and that relates to how low a frequency can you have telescopes on the ground in the radio. Then gamma rays. Gamma rays, we have telescopes in Ladakh and also in Panchmari. No, Panchmari. Now gamma rays, we have telescopes in Ladakh and Panchmari. How come that works? Does gamma ray is our atmosphere transparent to gamma ray or not? Is the atmosphere transparent to gamma rays? Can you detect gamma rays from outer space on Earth's surface? How many of you say no? How many of you say yes? And what do the others think? I will come there and ask you. Wait, hold on. This is not going to work. So, what do you all think? Is our atmosphere transparent to gamma rays or not? This side. Yes or no? Huh? Transparent. You all think so? No. Atmosphere is not transparent to gamma rays. Yeah, if atmosphere is transparent to gamma rays, again you are going to have cancer, right? So our atmosphere is not transparent to X-rays or gamma rays. But then we have gamma ray telescopes on the Earth's surface. So I'll tell you why. Or you tell me before I tell you. And then we also have cosmic rays. Cosmic rays are not light. All of this is light. Cosmic ray is particles, elementary particles, right? So protons, electrons, neutrons, alpha particles, helium, nuclei, and so on. So we also have detectors on the Earth's surface, including in Ooty, to detect them as well, right? So this is what we have right now, and then we have Aditya L1 in space, and I'll come to that. This is what we're planning, right? So we're planning to have a space telescope called Daksha to do X-ray astronomy. We're planning to have an ultraviolet telescope called INSIST in the future, and if you want to know about INSIST, he's the man to talk to. ISRO is planning to launch a telescope in space to study exoplanets, planets around other stars. We are planning to build a telescope just for the sun on in Ladakh. Okay. We're also planning a large optical telescope in Ladakh. We are planning to build a sublimeter telescope in again in Ladakh. What famous image came out of sublimeter astronomy recently? Terahertz sublimeter astronomy. Very famous image came in the front page of all your newspapers, including Star of Mysore, few years ago, taken from sublimeter telescopes. What is it? Millimeter or submillimeter? Yes. Absolute silence. This is silence people want in class in primary school, not at your age. What famous astronomy image came in the front page of papers recently? Okay, that's one answer. Any other answer? Sun. Any other? What are the famous big astronomy news in the last 5 years you've seen? What have you heard in the papers? Do you read newspapers? How many of you read newspapers? At least that you can put your hand. How many of you read newspapers? How many of you read papers? All of you don't, is it? My God, huge age-wise distinction. Okay, so the famous image of the black hole in the center of a galaxy and in front of M87 was taken in this waveguide. Okay, right. So this is a location of all the major observatories in India, right? So we'll go through each of them so that you know what to see when you go on holiday next, right? So in Hanle, in Ladakh, we have Hanle and Merak, right? And then in Uttarakhand, we have telescopes in Nainital and Devastal in the Himalayas. In Rajasthan, in Udaipur, we have a telescope in the middle of a lake. In Gujarat, we have on top of mountain Mount Abu, we have an observatory. In Maharashtra, we have the GMRT near Pune, and then there's this also the Giravali. In Tamil Nadu, we have Ooty Radio Telescope, Kodaikanal Observatory, and the Kavlur Observatory, Vainov Observatory, and then we also have this Gauribindo Radio Observatory in Karnataka. Okay, these are all on the ground. Have I left out anything? No, no. Okay, so we'll go through each of them one by one, just to tell you what is there in India. Okay, so our pride and joy of IIA is the Indian Astronomical Observatory in Hanle in Ladakh. It's around 6 hours drive from Leh towards the China border, and if you kind of not careful, you end up in China instead of coming to our observatory. This is 4,500 meters altitude, so it's one of the highest observatories in the world. It was built 25 years ago, at which point it was the highest observatory in the world. It has two optical telescopes. The Himalayan Chandra telescope is a 2-meter telescope. When I say 2 meter, what do I mean? Diameter of the mirror, right? Yesterday you had a talk about the mirror. Diameter is 2 meters. That's here. It is controlled remotely from Hoskote near Bangalore, because astronomers can't go to Hanle every day. So there's a skeletal engineer staff there, and it's controlled remotely. So if you get time on a telescope, you don't go to Ladakh, you go to Hoskote instead. Not as exciting, but that's okay. And then we also have the 70 centimeter Growth India telescope. This is a part of an international network of telescopes looking for asteroids, stars which explode, etc., all the time. And then we have two gamma ray telescopes. So just by reading it from the screen, can you now tell me how you can observe gamma rays from the Earth? Which physics one of these people get inspired by all these people? Which physics phenomenon, which is mentioned in the slide, is used to actually study gamma rays from the Earth's surface, though the atmosphere is not transparent to gamma? The answer is in the slide. You first row cannot say anything. What is Cherenkov radiation? Have you studied in nuclear physics? How large a speed to emit Cherenkov? How many of you heard of Cherenkov radiation? How many of you heard of Cherenkov radiation? So what do you think it is? Do you remember? Huh? Oh, back row. Excellent. So what do you remember? What is Cherenkov radiation? Correct, right? So you can't, I mean, you can't observe gamma rays coming from outer space because our atmosphere blocks it. Why does it block it? Because it always collides with one of the atoms and molecules of our atmosphere, right? And because the cross section is quite high to do that. So what happens is that if a gamma ray hits a particle in the atmosphere and that particle is accelerated to speeds higher than the speed of light in that medium, which is always possible, right? Not higher than 3 × 10⁸, but higher than light speed of light in that medium. I mean, no light is slower in media, right? Then it emits something called Cherenkov radiation in the extreme blue and ultraviolet, and this happens for like a fraction of a millisecond when the particle is moving very, very fast. And this brief flashes of millisecond duration light in the blue and ultraviolet is Cherenkov, and the blue part of it can be observed by these gigantic telescopes. So that's what it does. And then from the Cherenkov radiation, it will back calculate and figure out what the energy of the incoming gamma ray was, which led to this radiation. Okay. So this is the second largest telescope of its kind in the world, 21 meters in diameter, called MACE. And this is a set of instruments called Haga, which do pretty much the same thing. So, and then Hanley, the site is so good that many more telescopes are coming, including the submillimeter telescope, which I told you. Then the next, if you come down in latitude, is the Aries is Aryabhatta. What is Aries full? I always forget. What is Aries? Aryabhatta Research Institute of Experimental Science. But why is it E? Oh, okay. Observational sciences, right? So it's a DST institution in Nainital. It has an observatory in Nainital dating back to more than 50 years. It also has a new observatory in Devastal. Both of them are in the Himalayas. And Devastal currently hosts the largest telescope in India, a 4-meter liquid mirror telescope. Okay, and it can only look at the zenith. Why is that? Why? What is a liquid mirror telescope, and can it look at only a zenith? Again, this is all high school physics. Nothing new. No, not the first one. You cannot answer. No, I'm not telling them anything. So international. It's a liquid mirror telescope. What is it? What could it be? Yesterday, what did you learn from optics? For telescope, what do you need? You need a large aperture to collect a lot of light, and that aperture should be a focusing element, right? So, can you make a mirror out of liquid? So you can make a large tub full of liquid, but then it won't be a parabola or concave. How do you make it parabola? A large tub of liquid, how can you make it a parabolic shape? Rotate it. So if you rotate a liquid around, if you rotate a tub of water around its center, the shape of the water surface will be a parabola. Okay, this you can exercise for you to show. Okay, and then what you do is you take mercury, which is very poisonous, and then you spin it at a regular rate so that it's a parabola. And now, can you change what is the focal length of this telescope? What will it depend on? The focal length of this telescope, of this mirror? The speed at which you spin the telescope, right? The faster you spin, the shorter the focal length, right? And then you can, and then so that, and because it is liquid, you can only look up. If you try to look sideways, it's going to spill, and mercury is poisonous, so you can't do that, right? And therefore, they can only look at the zenith, and this is the largest telescope aperture in India right now. Okay, but the largest proper telescope which can move anywhere you want to is the 3.6-meter dot or Devastal optical telescope. It also has other telescopes which are a bit older as well in Nainital and Devastal. Now, we have a telescope in Kavalur, which is again dates back from the late 60s, called the Vainubappa Observatory, named after our founder Vainubappa. Okay. Now, this is the aerial view of it. So you can see each of these is a telescope by itself. The biggest is a 2.3-meter Vainubappa telescope. This is the biggest indigenously made telescope in India. In optical, the only large telescope made in India indigenously is this telescope, and that is this. You can go there and take a look. It open on Saturdays primarily. It also has a 1.3-meter J.C. Bhattacharya telescope. This telescope is 52 years old. A 1-meter telescope, which was famous because it was the telescope which discovered the rings of Uranus and the fact that Ganymede, a satellite of Jupiter, had an atmosphere. Okay, and it has a couple of other small instruments as well. Then PRL, Physical Research Laboratory, part of ISRO, has an observatory Mount Abu. It's good for infrared, and therefore they have a 2.3-meter telescope and a 1.2-meter telescope, and then they have other telescopes as well. And this observes in infrared because can infrared penetrate the atmosphere and come down to Earth, all of it? Any idea? So near infrared can come to Earth in some wave bands, but then mid infrared, etc., are absorbed primarily by water vapor in our atmosphere. Okay. Therefore, if you go to observatories which are high up, therefore less water vapor and very very dry locations like Hanle, Ladakh, then you can observe more than near infrared. And Mount Abu in of PRL is one of them. Okay. And then IUCA also has a telescope in Giravali near Pune, which is I think currently not functional. Then, currently IIA is celebrating the 125th anniversary of Kodaikanal Solar Observatory. It's one of the longest running solar observatories in the world. It has one of the longest continuous daily records of the sun in the world, apart from one more observatory in the US. It has all these instruments to study only the sun, and was established by the British in 1899. So next time you go to Kodaikanal for your vacation, you know what to do. It's also open to visitors every day. It has a museum for you to go to. It's an astronomy museum which has a lot of really cool stuff for you to look at. So please go do that as well. Okay. India is fairly big in solar astronomy, partly because we are tropics, unlike these cold Scandinavian countries where they don't see the sun at all, and therefore we have quite a few solar observatories around India. Okay, so the other big solar observatory is the Udaipur Solar Observatory in Physical Observatory. That's in an island in the middle of a lake. Okay. Why would they want to do that? Based on what you heard yesterday in your talks, why would you want to put a telescope in the middle of a lake? What could be the reason? What kind of? So the water has a huge heat capacity, right? So it kind of stabilizes. It also stabilizes the air pattern around the telescope. The atmosphere over the telescope is stabler, and there's less convection due to heat and so on. If there's a water body. Okay, so then that's partly the reason why it's here. It's also a very fairly old site, and that they do basically solar astronomy. One is MAST and the other is GONG. GONG is a part of an international observatory. So it's exactly the same. The GONG is a set of 8 or 9 exactly similar telescopes placed around the world. One of them is in Udaipur in India, and they look at how the sun vibrates in real time. Okay, it's called helioseismology. Then in the what I meant to okay. Then the radio. The radio is probably the wavelength where India can compete internationally in terms of one of the best telescopes in the world. The UT telescope, I'll come to this first. So both of these are run by the National Center for Radio Astrophysics in Pune, which is under Tata Institute of Fundamental Research. The UT telescope is this. It was built in 1971, and at that time it was the world's largest telescope. Okay, so to build the world's largest anything in India in 1971, you can imagine it's not an easy thing to do, and therefore it's a huge achievement. And it has done a lot of really good stuff since then, including, for example, providing one of the early evidences for the Big Bang theory versus steady state theory. Okay, it's in this direction is 30 meters in diameter, a parabola, and in this direction it's half a kilometer. So if you look at Google Maps and go to Uti, you see the telescope of Google Maps very easily because it's half a kilometer long. It's as big as a hill. It's on the hill. Okay, and tomorrow you can maybe talk about why it's on the hill. That's part of your spherical astronomy. So tomorrow morning we'll tell you why this hill, what is special about this hill. Okay. So this is a it was the largest telescope. Now it's still one of the world's largest radio telescopes among the many. But then when it was built, it was the world's largest for many years. Currently, the largest telescope we have in India on the radio is called the Giant Meteor Radio Telescope. It's in Khodad, the village near Pune, between Pune and Nashik in Maharashtra. And this was again the world's largest telescope. It was built in 1998, and it continues to be one of the largest telescopes in the world at its frequency. It's a different telescope than this. It's made of 30 dishes, 30 like your satellite dishes. Each dish you can see is 45 meters in diameter. You can make out the SUV here, so for scale you can see how big that each telescope is, and it's spread over 25 kilometers. Okay, and along with the Himalayan Chandra Telescope in Hanle, this is one of the 2 telescopes in India which are and AstroSat, which is up in space. There are 3 telescopes which are open to everybody across the world to use it. The half of the time is used by people outside India, half the time is used by people inside India. The GMRT. Okay, and then we, along with Raman Institute, have an observatory in Gauribidanur, which has a lot of telescopes at low frequency to observe the sun and pulsars. These are all dipole arrays, which are like your TV antennas of yours. Okay. Then All this is what we have on the ground. Now we also have space observatories. ISRO launched something called AstroSat in 2015. We're going to celebrate its 10th year now. It is AstroSat, and it has 4 telescopes looking at the same direction at the same time. So if something happens in the sky, you can look at it with all 4 telescopes at the same time because they all align to each other optically, right? The biggest of them is the ultraviolet imaging telescope, which we built, IIA built in Hoskote, and this is the exact engineering replica model, 2-scale model of the ultraviolet imaging telescope in our institution in Bangalore. You can see how big it is, and that is just these two cylinders you see here. That is this. The rest of it is made of 3 other telescopes to do imaging and photon counting in the soft X-ray and hard X-ray. So AstroSat is very important because it can look at ultraviolet, soft X-ray, and hard X-ray at the same time in the same direction, and is usually used to study star formation, but also things which go boom suddenly, like supernovae, novae, things which explode, things with and very high energy phenomenon, and something explodes in real time and varies over time, over minutes or seconds or hours. To be able to study them, how this varies in ultraviolet up to hard X-ray is a very, very important thing to do. So that's one of its main advantages. Then last year we launched Aditya L1. How many of you heard of Aditya L1? All of you did. Okay. So there's a lot of press about this. So this was launched by ISRO last year to study the sun. It's a solar space mission with seven payloads. One of them is the visible emission line coronagraph, which is here, which was made by IIA in Hoskote. Then there's the imaging telescope in ultraviolet, and then X-ray spectrometers, particle and mass spectrometers. You know mass spectrometers in nuclear physics. So there are 2 mass spectrometers, 2 X-ray spectrometers, ultraviolet imaging telescope, a visible line coronagraph, and a magnetometer to measure the magnetic field of the plasma from the sun as it goes on. You'll learn much more about it tomorrow in Ravindra's talk. Okay. Now, what's coming soon? Now then ExpoSat, of course. Then okay, there is also more space observatories. ExpoSat was launched last year by Raman Institute, primarily to do X-ray polarimetry of high energy sources in the sky. Chandrayaan 1, 2, 3. All of you know about Chandrayaan 1, 2, 3. We count them under astronomy. We claim them too. Mangalyaan, and then Shukrayaan is coming up. The ISRO's proposed launch to Venus, and Chandrayaan 4, 5, 6 are also being planned, right? One of them will also return samples from the moon for the first time for India. Okay. Then India is also involved in many other projects. What's the time? Then I what? Half an hour more? 40 minutes more? Okay. International mega projects. So we are also so these are telescopes which are functioning already. But then if you want for the future, we want new telescopes. We want bigger telescopes to cover multiple wavebands, etc. To have multiple capacities. So the 2 or 3 mega projects, international projects, which we are a part of, and why we are part of international projects is that the telescopes we have now in India and around the world are about as big as you can get if you want to build it as one institution or one country. The next generation telescopes are going to be so big and therefore so expensive. You need multiple countries to come together, not just because of money, but also because of skills, experience, and so on. And therefore, they all international telescopes, right? So, one of them is the Square Kilometer Array. The Square Kilometer Array is going to be the world's next largest radio telescope. Half of it is in South Africa, half of it is in Australia, and the first part of it is going to be already around 15, 20 times as large as the largest telescope we have in the radio in the world. The full one will be a couple of 100 times bigger. Okay. So the GMRT near Pune is a pathfinder for this telescope. A lot of work happens in India for this because India is one of the 13 or 14 partner countries from the beginning, from the inception of this project. We don't just give money. We don't send money through UPI or something. We actually build things for the telescope, right? So one of the biggest, so India is leading, for example, the entire control software for the entire telescope. We are designing and making it with Indian industry. We are also leading some of the design and manufacture of some of the low frequency dipole antennas for the Square Kilometer Array, which will be deployed in Australia. Okay, and all of it is being done led by NCRA in Pune, but then along with Indian industry. The second thing which IIA is leading is the 30-meter telescope. So I told you the largest physical aperture of a full telescope in India is 3.6 meters. But do you know how big is the largest telescope in the world? Did Arun tell you yesterday? 10 meters, right? So 10 is the largest we can go to. And even that is typically made of multiple mirrors, segmented mirrors put together. It's very difficult to go beyond that. So the next generation optical telescope, the 3 big ones being planned, One is the 42 meter, 42, right? By Europe, by European consortium called the Extremely Large Telescope. It's a very obvious name. Then there's the 30-meter telescope being proposed with 5 countries, and then there's a third telescope called the GMT. Okay. Now this again will be, the diameter of the mirror will be 30 meters, but then you can't again cast a mirror that is 30 meters in diameter without breaking it, and also be able to move it in one go very precisely in the sky. And therefore, this is going to be made of 496 individual hexagons, each of which are around 1.4 meters in diameter, right? So you can imagine 496 segments put together to form a 30 meter. 30 meter is probably bigger than this length of this room, right? The mirror itself is going to be that big, and the telescope is going to be on top of that, right? And therefore, the 5 countries, now 4 countries making it. India is one of them, and IIA is the leading the Indian effort. So what are we doing? Again, we're not sending a blank check. We are making things for the telescope. So we have something called the India TMT Optics Fabrication Facility in Hoskote, which you're welcome to come and visit. Where of the 496 mirrors, 80 of them will be made here. We'll probably end up making more than 80. Are being made here along with Indian industry. We also, all the 496 individual mirrors, they cannot be looking at different places, different directions. They all be looking in the same direction. But then the alignment with respect to adjacent mirrors has to be a few tens of nanometers, right? And to do that across 30 meters over 496 segments, you can imagine it's not a trivial task, engineering task. It is one of the most precise optical tasks, optical things to be ever done in the world. And therefore, each of the 496 mirrors will be backed by a support assembly, which will detect how if it is deviating from the full 30-meter exact shape by a few nanometers and correct it every few milliseconds. Okay, that is the precision needed, and all of the 496 ones are being made in India with with industry participation. So that's a huge engineering feat. I think one of the most precise things India has ever made so far in any field of engineering. And of course, we are going to make control software because we are good at that, right? So this is how it look like when it's done. Okay, and the third is LIGO. LIGO, all of you know LIGO, gravitational waves, right? 2 of them in the US detected the first gravitational waves. There's going to be an exact replica of the 2 LIGOs in India, in Maharashtra, near Nanded, near Hingoli, called LIGO India, and that's all in partnership with the US. So we're going to have an exact replica of what the 2 LIGOs in US have, and and there's already been, the construction has already started. The reason you're doing that is that the LIGO, if LIGO detects an object, you don't know where it's coming from. One LIGO detects something, you don't know where it's coming. It could come from anywhere in the sky, right? You don't, because it's not an optical telescope where pointing in one direction. Gravitational waves from any direction, all entire 4 pi steradian, even from bottom of the earth, can pass through and then affect your detector. So you don't know where it's coming from. If you have 2 of them, then you can triangulate a little bit and see where it's coming from, right? If you have 3 or 4, then you can triangulate more and more and more. And if you look at where all the gravitational wave detectors in India, in the world are, 2 in the US, 1 in Italy, 1 in Japan, etc. The ability to detect, to localize the position in the sky from where the gravitational wave is coming from, so that you can point your optical telescopes and find out exactly where it's coming from, is very limited. By adding one in India, because of the geographical longitude, latitude spread of where India is with respect to other detectors in the world, you can actually you can get the location of where it's coming from much more accurately. So it's going to be very important for that. Okay. Then then mega projects await. These are all what already been approved in some sense, as in we have money from the government. These are what are awaiting approval. For example, we're going to build a 2-meter solar telescope on the banks of Pangong Tso in Ladakh. Pangong Tso, all of you know. How have you been to Ladakh for like vacation? How many have you seen Three Idiots? Last scene there's a lake, right? That is Pangong. So we're going to have a telescope there. Okay. So that's awaiting approval. Then Daksha is going to be a space telescope in the X-ray, which is again awaiting approval to be launched. This is being done by IIT Bombay. And then I told you there's a Cherenkov 21-meter size Cherenkov detector in Hanle in Ladakh. The proposal is to build 4 more of them. Okay. First the Maze 2, then Maze 3, 4, 5, and so on. We're also proposing a large 6 to 10-meter class diameter optical telescope in Ladakh. That will be then India's largest telescope to compete with what other countries have. There's a proposed space telescope to be in ultraviolet as a follow-up to AstroSat. which would in principle be able to make images with the resolution of the Hubble Space Telescope, but in the ultraviolet. And then these are all the other telescopes which are being proposed right now, which are under approval or under study, right? So there's something to look at: the cosmic microwave background radiation, which Subunya talked about yesterday, exoplanets, subliminal telescope, which will hopefully then join the Event Horizon telescope to make the black hole image, a telescope to orbit the moon, and so on and so forth. So a lot of attempts are being made by astronomers across India to make sure that we either make or are a part of the next generation of telescopes in almost every way back, right? Uh, and it's a slow process. It's a torturous part. If you ask Mahesh, I'll tell you, it's not an easy thing to propose a telescope, get funding, and start. It's a very very long path. But that's something almost every institute in India is doing. Okay. Now how do you become an astronomer? Right. So I just want to tell you a little bit about that. The most common path of astronomer, if you look at any most astronomers in India, and you ask them how they became an astronomer or a faculty or a professor, they would do a BSc Physics, MSc Physics, PhD in astrophysics, then do a postdoctoral fellowship, always similar to any branch in physics, in science, of course. But usually they don't do a MSc in astronomy, they do a BSc in MSc in physics. And I think that's important to tell your students as well and your colleagues as well. If you want to do astronomy, it's important to get your physics background done. So it's important to have a good grounding in physics and then come to astronomy and then do a postdoctoral fellowship, then you become professor and then you retire and then you die, right? But then but then you can also, instead of doing a BSc in MSc Physics, you can also do engineering and then come to astronomy as well. You can come to a PhD in astronomy after BE. You can do a PhD in any branch of physics. I think there's one thing these 3 days should teach you is that astronomy is nothing but applied physics, a branch of physics. And therefore, if you're really good in one branch of physics, astronomy is a subject which is capable of using every branch of physics, right? So if you do solid state, condensed matter, particle physics, nuclear physics, statistical mechanics, whatever you do, there's an astronomy will use all of it. Will use you basically, right? And therefore, you can always shift from any PhD. Uh, and then move to astronomy later as well. If you come to astronomy with a solid background in physics, in a branch of physics which is very useful, which is having a lot of applications. For example, you could be doing general relativity all your life, and then suddenly you have a gravitational detector, right? Then or if you're studying nuclear physics and you're looking at quark gluon plasma, and then the neutron star astronomer would be like, please come and work with me. We want to understand what's the center of neutrons. Right? So there's so many applications of every branch of physics. So it's not needed that you have to do astronomy from the beginning. You can always jump to astronomy later, and I think that's important. Why? Because a modern astronomer needs modern astronomy, and a modern astronomer needs a little bit of everything, right? Most astronomers mainly focus on this and get a little bit of knowledge here, but then you could come from any of these as well. I want to impress that upon you, right? So, no, we need people to design and build our telescopes. You need engineers and technology people. You need people who understand optics and detectors, solid state devices, the latest detector technology, CMOS, what have you, right? You need people who can, our telescopes right now currently already give you terabytes of data a day, right? And the future telescope I told you about, like the square kilometer array, 30-meter telescope, will give you petabytes of data a day, right? Therefore, handling all of that is not easy. There's no point of having a telescope when you can't look at the data, because data just swamps you every day, right? If you're having petabytes of data a day, you need to have people experts in big data, in high performance computing, in supercomputing, and in devices, in computing devices, and so on and so forth. All of this. So any large astronomy institution or observatory will employ people from all of these backgrounds, and that's something I want to tell you. Chemistry as well. Astrochemistry is a large part of astrochemistry is becoming more and more important, and I think Mahesh will talk a little bit about it. You'll hear a little more in the afternoon about how astrochemistry is important, right? I don't understand any chemistry at all. I forgot all my chemistry after 12, and therefore you ask me what happens in the middle of a molecular cloud so star can be formed. I'll ask a chemist friend to tell me about it, right? Biology as well, yeah. And not just because you'll find aliens. Astrobiology is not about how many legs and feet an alien has. Astrobiology is about how does life form? How do amino acids form? What does it take? What kind of physical properties should a planet orbiting a other star have, so that there's a probability of having amino acids and then them coming together and forming the first signs of life are possible, and so on. All that is biology as well, right? So what I did was I just took all the, and therefore astronomy covers a large gamut of scales, of sizes, of times, etc. I just took all the research areas of astronomers who just work in my institution in IIA, and I put them all together. And this is pretty much covers everything except 4 or 5 major areas. Everything else is covered, right? So you can imagine just in one institute, we are probably the largest institute of astronomy in the country. And except for 4 or 5 areas, we have people working on every area, right? And all of these are connected, of course, and all of these basically depend on what everybody on this in the side of the room did, right? Not you people. I mean the ones whose posters, whose pictures are here, right? Um, so where can you do astronomy, right? This is not just for you, but maybe for your friends, for your students, and so on. So you can. So of course, no, India, we have this two-tier system. We have research institutions which are well funded, and then you have universities which are not. And therefore, we have research institutions. We have 4 of them who are dedicated almost completely to astronomy only, right? So we are the largest. Then there's the Inter-University Center for Astronomy and Astrophysics, IUCA in Pune. How many of you heard of IUCA? So this is important for you. I'll come back to this in a bit. Then there's a National Center for Radio Astrophysics in Pune, and then ARIES in Nainital. These are either completely or almost very, very largely focused only on astronomy. And then there are also research institutions which have a large department only for astronomy, like TAFR in Bombay, ICTS in Bangalore, PRL and Udaipur Solar Observatory, ISRO, IAC, Raman Research Institute, SN Bose Institute in Calcutta, Bose Institute in Calcutta, Saha Institute in Calcutta, and so on and so on. Right? Then, in addition, there are many institutes and universities which now have a smaller department for astronomy, a smaller department in universities, not just research institutions, right? So outside, no, like fancy institutes like Tata Institute, many universities now are having astronomy departments. And this is a list of this probably fully almost complete, not quite complete, and quite a few already. Right? IIT Indore has an entire department of astronomy. IIT Kanpur, IISc Trivandrum, IISc Calcutta, Presidency Calcutta, Osmania in Hyderabad, Manipal, Christ University in Bangalore, Delhi University, and so on, right? So all of these are universities which have an astronomy department outside their physics department or as a part of the physics department. And then you have, of course, universities where in the physics department there are one or two or three or four astronomy faculty who are part of the general physics department. And why this is important is that then when you do an MSc physics course in any of these, the astronomy faculty will offer you a paper in astrophysics. So you don't have to do, so you can start studying astronomy already in MSc if you're in one of these places and the faculty there offers a paper in your last year as an elective paper in astronomy, for example, right? But more importantly for people in the university system, yeah. And then of course, there are visiting student programs, the summer schools and inter schools, internship programs, etc. These are aimed at BSc third year and MSc students. But then some of them are also applicable to, a few of them also applicable to young faculty and early career researchers as well. But the more important thing for all of you is the IUCA Research Associate Program. IUCA is the so UGC has around 6 inter-university centers on different topics in science. There's one in nuclear physics, there's one in biology, there's one in, I forget what the others are. But the one in astronomy is fairly old, it's almost 30 years old. And it's in Pune. Okay, so that's the IUCA, Inter-University Center for Astronomy and Astrophysics. So one of the mandates is to promote astronomy in universities and in colleges across India. And they do a really good job of it. And that's why I think it's important that you know about it, right? And the way to do that is the associate program, where if you're a faculty member teaching in any college or a university anywhere in India and you're interested in pursuing astronomy for research or to teach it, then you can apply to be an associate. Currently they have 264 associates across India, spreading from Nagaland to Daman Diu to Kashmir to Tamil Nadu. Okay, and therefore, and this is one. So please go look at this program, see what the requirements are, see what it takes to be a part of the program. What you then get is a lot of support from IUCA to do research in your spare time, because we know that the teaching load is just humongous for the teachers and lecturers. And therefore, in your spare time, in summer, in your vacation, you can go to IUCA. They have introductory astronomy workshops, a lot more rigorous than what we're having, and for extending over 2 weeks, aimed at college lecturers to get them into astronomy, and then they'll handhold you and support you in starting research or teaching astronomy. If you want to teach astronomy in your college, they help you with that and so on. So it's very important for the young lecturers to look at, and I do suggest that you do that. Okay. And of course, no, there are other ways of being an astronomer too. A lot of the radio astronomers in India, the older generation, used to be engineers who shifted, and that we need them because of new observatories. Like I said, we need people in high performance computing, big data, etc., etc. Even project management, system engineering, all of it, astrochemistry and astrobiology. These are all fields. These are all new. These are all ways in which you can engage in astronomy without necessarily being an astrophysicist after doing an MSc physics. Right? That's important to know. And not just that, we also now, like I showed you many examples, many of these big projects we are doing, we don't make the telescopes or parts ourselves. We work with Indian industry, and therefore a lot of Indian industry is hiring people who have a background in physics or even astronomy to help them, in these large projects they take contracts for, right? So, for example, the Astronomical Society of India, which is the ASI, which is the other ASI, we are a better ASI. For last 3 years in our annual meetings, we had an entire session with where we invite industry people to come and talk to our students, PhD students, postdoctoral fellows, about if you want to transition to industry and still have a connection with astronomy or with large engineering projects, even large physics projects like the ITER, right? The fusion reactor in France, which India is a part of, and so on and so forth, or the synchrotron facility called FAIR, etc. Then that's another way to do it, right? Uh, the other ways of practicing astronomy or science in general, not just astronomy, there are science. We have around 50 planetaria in India. We have some 70 odd science centers in India. We are building a planetarium in Mysore. Do you know about that? How many of you heard of the fact that we're building a planetarium in Mysore? Most of you haven't. Oh, that's really pretty. So you should look at the flyers we're giving you here. So we're building. Our institute is building a planetarium in the University of Mysore campus in Tavarekare called Cosmos, right? So the and then science centers and planetaria need people who come from a science background but who love science communication, who love to popularize science. We need people like that, right? We are many institutions, many research institutions and projects in all over science, biology, chemistry, physics are now employing people for science communication, for outreach. Observatories, large projects, large science projects need people to run them. You need people who can run the instruments, who understand them, and so on, right? Then there's a lot of work that we done on history of astronomy, right? So that combines knowing maths and astronomy, but also ancient languages. So, for example, Yashaswini here has been working with some experts in Bangalore. We had somebody called Puneet here earlier, who's now working with the Oriental Research Institute. How many of you know ORI in Mysore? You're from Mysore, right? How many of you are not from Mysore? Okay. The Oriental Research Institute is a part of the University of Mysore, and it's an absolutely amazing place. You have to go see it. You go to the main room, and what you see is a room twice as big as this, filled with palm leaf manuscripts from the last, I don't know, like 1,500 years. Okay, and that's there right here in Mysore, and it is one of the biggest collection of old manuscripts in the country, right? And it's from all over the country. A lot of them are in various languages and various scripts, and is run by the university. So please go take a look. It's right in the middle of the city. Right? Where is it in the middle of the city? Opposite Crawford Hall. There you go. So go see it. I mean, so we have a team of people working with the Oriental Research Institute. We have identified 48 astronomy manuscripts in paper and palm leaf dating back to up to 9th century, which has not been studied by anyone so far, right? So and that's so we're working with linguistics experts. We're working with the Kannada department. We're working with BM Sri Pratishtana. We're working with people who are experts in linguistics in Hale Kannada, in maths, in ancient Indian astronomy, in modern astronomy, etc., to put all this together, right? So many other ways in which you can engage as well, right? Okay. Now, how much time do I have left? 20 minutes. Okay. So I finished my spiel about doing astronomy in India. Okay. Now I have 4 or 5 questions about related to Mahesh's talk in the morning. Before we do that, are there any questions or comments about what I said so far?
Laboratory
Yeah. What about it specifically?
the largest telescope.
It's not the largest. It was the largest telescope many decades already.
Any linkage?
There's no linkage. Mount Wilson in Mount Wilson Observatory is it came in the news recently, 2 weeks ago. You know why? It was the part of the forest fires in Los Angeles. So it is an observatory built around 150 years ago. That time outside Los Angeles, and now of course in the city on top of a hill. And if you look at many action movies, many action movies which are made in Hollywood, if you usually there's a climax scene or a starting scene on top of a hill with a white dome building, that is the Mount Wilson Observatory. And the reason it is one of the largest telescopes, like many decades ago. But Mount Wilson and our Kodaikanal Solar Observatory are the two observatories with the longest daily records of the sun in the world. So that's one connection. Other questions, comments about about the telescopes, about the technology, about how they work, about what is happening in India, anything? If not, then it's question time. Uh, so different the seven instruments, different instruments are performing are giving results at different rates. Uh, the imaging ultraviolet imaging telescope made by IUCA, you can look at the website if they have some images. The visible emission and coronagraph, which we have, only the spectrometer, one spectral line channel is working, and that is available now. So all the seven payload data is now available on in ISRO website from uh, what NASDC, what's it called? There's an archive of all the ISRO data. So all the data are available there. Many of them might not be might be in a format which you can't access readily. So the coronagraph spectral line images are coming up soon, but then not, everything else there's a problem. They're working with it. The imaging ultraviolet imaging telescope images are available, which you can look at from the ISRO site as well as from the SUIT website itself. The X-ray spectrometer as well as the mass spectrometer data and the magnetometer data are also on the ISRO website. But then they will not be in a file. They will give it. It'll all be there, but then the file format might not be in a way which you can readily open and see. You might need to have extra software to analyze it. So then you have to talk to the people in charge for that.
Respond basket gives a list of projects funded by ISRO to the center.
Yeah.
Respond basket.
Other questions, especially from the back. Okay, then let's run through the five or six ones. Mahesh. Okay, right. So how many of you have laptops here? Calculate phones are calculators. Okay, one volunteer to come to the board. So this is a question. The so what is the now he talked about fusion, right? Now why don't you get fusion if I just like throw protons together in this room? The electrostatic repulsion, right? So I had to overcome the electrostatic repulsion, get them close enough that the strong nuclear force can take over, and then it can fuse potentially, right? So the Coulomb barrier, in some sense, for two protons to merge is around 0.6 MeV. Okay, so if you assume ideal gas, Boltzmann distribution, etc., what is the temperature needed for the average kinetic energy to be 0.6 MeV? How do you calculate this? This is the Coulomb barrier energy, right? So this is the average kinetic energy as well. So that any two protons, if they have more energy, then they could overcome the Coulomb barrier in principle and and fuse to form and do nuclear fusion, right? So for this to happen, how does this relate to the temperature of the gas? The average kinetic energy and the temperature. This is not astronomy. This is thermodynamics. Huh? Huh. Free particles. So let's say how many degrees of freedom you want? Three. Come. No, come to the board. Come, we'll see. No, come. We'll all help you. We'll all help you. Come. Somebody has to come to the board. Who will come to the board? We'll help you. You want K? No, K value, somebody will tell you. Come. No, come. Somebody has to come. Or I will choose. No, you do the first. The second question onwards, I'll ask somebody else. Okay? Come. Come. There you go. You've been very brave so far. Okay, yeah, so what is if the average kinetic energy, how is it linked to temperature and ideal, Boltzmann distribution? The gas is Maxwell Boltzmann distributed in energy, in velocities. 3 by 2 kT. Okay. So now this is 0.6 MeV. So what should T be? What is K? Somebody Google, no? I forgot it. Huh. So T. Huh. You can throw away 3 by 2 equals 1. In astronomy, we do things like 3 by 2 equals 1, 2 equals 1, 6 equals 10, 2.3 equals 1. We do all that. It's okay. Order of magnitude calculation. I don't care. It's okay. MeV, yes. So temperature. So MeV you need to convert to joules. Will this write better? This writes better. The next question, the next person I will call. Or I'll ask ma'am to decide whom to call. So what do you get? Others, please see if it's right or wrong. So like I said, put 2 equals 1, 3, 2 by 3 is 1 and all. It's okay. See, this is 0.2 into 2 is 0.4 into 1 So make it all 1. Remove all the numbers. Just have the exponents. Order of magnitude. Sun is so big, yeah, 2, 3 and all also. Doesn't matter. We'll ignore. What is the temperature at the center of the sun? What is the temperature at the surface of the sun? How hot is the surface of the sun? 6000 Kelvin, 5700 something like that. Are you getting 10 power minus 33 Kelvin? Kelvin. You know how small the temperature is. That means it will happen everywhere, no? Then it should be happening right now in front of me. In fact, it's too hot for fusion to happen. We are 30 Kelvin. We are 300 Kelvin. So something is wrong, no? What went wrong? So what's the energy? Energy is 0.6.
MeV.
M is 6. EV is
1.6 into 10 power minus 19.
19. That is 3 by 2. 3 by 2 is 1. What is K?
That is 1.3 into 10 power 23 no minus
23.
minus only.
Minus 23, no?
Yeah.
So then what is this? That's it. So then what is this? Throw away all the 1.3s and then done. What's the order of magnitude? Correct. 10 power 10 is correct. Yes, you're right. Right.
I have done this. I kept it in the numerator. Sorry.
So what is this? Is it 4, 4 or 10? 10. So write it. So plus 10. 10 power 10. Here nobody understands what you're saying. Write it here, no? Nicely. Kelvin. The temperature at the center of the sun is around 10 million. 10 power 7 Kelvin. Can you write 10 power 7 Kelvin? So can you write 10 power 7 Kelvin somewhere? The actual temperature of the center of the sun is 10 power 7 Kelvin. 1000 times cooler. So why is the sun shining? Thanks. Thank you. Applause for her. The first person of many of you to come to the board. So the center of the sun is 1000 times cooler than is needed for 2 protons to cross the Coulomb barrier and fuse. So then why is the sun shining? But it happens now. 2 protons are fusing now. Because why is it 2 protons? Why do you know 2 protons are fusing? Because we see the sun. Something is happening. Some other workaround is happening. What is the workaround? This is nuclear physics. No fission. Fusion. So we know that protons fuse to the center of the sun. Because when you get up in the morning, sun is rising and it's bright. But we know that the temperature is 1000 times less than what is needed to cross a Coulomb barrier. So then what could be going on to actually cause fusion? This is quantum mechanics 1, quantum mechanics 101 and little bit of nuclear fusion 101 put together. Was it covered? No. I think they might cover in the afternoon. Okay, but then this is not astrophysics. This is a problem in quantum mechanics and nuclear physics. We have a potential barrier. I'm giving you a lot of hints. Okay, Coulomb is a potential barrier. Coulomb potential barrier. So the electron, one electron sitting, other electron cannot overcome the barrier because it doesn't have enough temperature, which means it doesn't have enough energy to cross the barrier. But somehow it happens. First row cannot answer. Somehow it crosses the barrier and goes inside and fuses. Correct. Who was it tunneling? Put your hand up. Ma'am, you also put your hand. You also no. So correct. So the answer is quantum mechanical tunneling. So the sun shines only because quantum mechanical tunneling allows a fraction of the protons to cross the barrier, even though they don't have enough energy. Okay, so that's amazing, no? This is very surprising, isn't it? So your tunneling was a painful thing in your assignment. You had to solve it, and you didn't know why it was there. No application for quantum tunneling ever given to you. Completely bizarre thing which you couldn't even believe is true. The sun shines because of quantum tunneling. So that's very important, isn't it? Okay. Now, why does fusing heavier nuclei need higher temperature? Now he said, now hydrogen forms helium, helium will fuse to form carbon, carbon nitrogen will fuse to form neon, neon sulfur will fuse to form etc. up to iron. Now forget tunneling, go back to Coulomb barrier. Why would fusing heavier nuclei need heavier and heavier nuclei fusion will need heavier and heavier temperature? Why? Why? So why is the barrier more for? Hmm. How does it go with? So how does it depend on the nucleus, the Coulomb barrier? You all do nuclear physics, no? So if a nucleus is there for higher atomic number nucleus, how does a Coulomb barrier go? What's the dependence roughly? But what is the how does it go? What is the functional formula? Huh? Proportional. It's proportional Z1 Z2, right? The charge of one times charge of the other, right? And therefore, heavy nuclei also require higher temperatures. Okay, right. Then now one more person has to come. Who will come to the board? Next person. Huh? Somebody has to come to the board and do quickly before lunchtime. You're all hungry. Okay, come, please. Okay. Now, have you heard of Sirius? Sirius is the brightest star in the sky. Okay, it is the brightest star. If you go now if you go in the evening in the eastern sky, you can see Sirius very bright. Canis Major. Okay, big dog. Because Canis Major and Canis Minor, small dog, are helping Orion the hunter fight Taurus the bull. That's the story on the sky. Okay, in the Greek mythology. Now, if you look at Sirius through a telescope, large telescope, you'll see that very close to the very bright Sirius is a small fainter star called Sirius B. And Sirius A and Sirius B we know are going around each other. They are bound, they are gravitationally bound double stars going around each other. Okay. Now Sirius A is the bright thing. Forget that. Sirius B, the companion star to the brightest star in the sky, and they form a double star. All this is actual numbers. The surface temperature of Sirius B is measured to be 25,200 Kelvin. How do you know this? How can you measure the surface temperature? How can you measure the surface temperature of a star? Lambda max T is 0.3 something. Okay. And is seen to emit as a black body. Okay, its luminosity is 0.026 times the luminosity of the sun, which is given by this. Sigma is this. What is the radius? Yeah. Like I said, again 2, 3 and all you throw away. I want rough. First write the formula. If it is a black body, then the luminosity is proportional to nothing but its temperature and nothing else. No composition can enter into the picture, and 4 pi r square is the total surface area. Right? Sigma T power 4. Square root. Okay. Fine. Okay, fine. Okay. Now can we put everything in and see? 4 pi is 10. 4 into pi is 10. No, you know that 4 pi is 10. Okay. 3.8 is 5. 5.8 is 10. Whatever. I don't care. Or if somebody wants to take out their phone calculator and then tell them the actual numbers, that will actually be nice. Luminosity is 0.026 is 3% of the solar luminosity. Its brightness is only 3% of the solar luminosity, but it's very hot. Now we want to see how big it is. You see. No, not quite. I think it's thrown away too many factors. The trick is to know exactly how many factors throw away and not more than that. Okay. All of this somebody can calculate on the phone and tell you. Okay. 0.026 times the solar luminosity is 4 10 power 26 watts. watts. Okay, fine. Then 4 pi sigma T power 4, 25,200 or 4. Okay, right. So can do 2.52 per 4 and then 10 power 4, then 10 power 4 times 4, 10 power 16 you take up. Somebody can do 2.52 per 4, all the small numbers somebody do for her, no, please. Take out a calculator, somebody and do. So 0.026 divided by 10 divided by 5.86 divided by 2.52 to the power of 4. Somebody please do for her. The power, all the 10 powers and times 4, all the 10 powers you do. What else is happening? Minus 7. And then this is there, no? So make it 2.52 and then take 10 power 4, 416 up. Easier for you. 2.52 per 4. 16. Sorry. This 4 don't forget. This 4 will give you quite a large number. Hmm. This is R squared, by the way, not R. Hmm.
Make it 2.2 minus 2 and cut it 5.8.
But then the minus 2 you have to put. So minus 2. Don't actually solve problems this way in exam, okay? You totally fail. Do it properly. So bottom is 40, right? 2.5, 2.5, 6.25, 6 squared is 36, so 40. Upar, what's the exponent on top? 15. 15 and then, so you can take one more zero, roughly 14. Nah? You're getting roughly the correct answer. Okay, R squared. So R is? And then R is 10 power 8. What units? Meters. So kilometers? Actually, the answer is half of that. You're very close. It's actually half of that. Okay, it's 5,000 kilometers. You got 10,000. So pretty good. Oh no, you got 100,000. Sorry, you're off by a factor of 20. Answer is I calculated yesterday. It's 5,784 kilometers. You put all the factors, you'll get some 10. Never mind. Roughly in a ballpark, right? So series B is shining at 3% the brightness of the sun, but it's 5,700 kilometers in radius. What's the radius of the Earth? 6,000. So this is as big as the Earth, right? Is that correct? Does it make sense? Something we are getting the size of the star, which is 3. Sun is very bright. 3% of the sun is also very bright. 3% of the sun, but it's as big as the Earth. Isn't that weird? Can it be right? Which of these people is it linked to? Another question. Which of these people is this answer linked to? There's one person in here whose answer is who's famous for exactly this. Exactly this. Why? Okay. Now, the mass is this. Okay, 2 10 per 30 kg. Okay. And so what is the density? Do you want to calculate? Okay, board, I'll do it myself. This is 10 power 9 kg per meter cube. Now, you all done solid state physics. So what matter is 10 power, roughly 10 power 9 kg per meter cube density? What could it be? linked to Chandrasekhar. This is total Chandrasekhar connection. So what can it be? What is the density of like Earth? Roughly. Density of Earth, yeah. Rock. How much is it? Water. What's the density of water?
1,000.
Back, nothing. What is the density of water? Density and unit. What is the density of water? These two rows. Density of water. How much is it? 1,000 kg per meter cube. Correct. Rock is, Earth is how much? 2 times, maybe, I know how much, 10 times more. 10 times more. This is a billion kg per meter cube. So, I now want to tell you, you find out, or somebody will tell you later, what kind of a star, which is, a few percent as bright as the sun, as big as the Earth, has density a billion kg per meter cube, around a million times that of water. I'm not going to tell you the answer. Wait, try and figure out. Okay, then the next question.
So this spoon of that
Hmm. Yeah. 1 meter cube is this much, no? That's a billion kg. That means this much will be like a million kg. This much is a million kg. What matter, what state of matter in your solid state physics have you learnt where this much is million kg? Plasma is very, very rare. It's very low density. Right? It's other extreme, right? Like the sun. Right? This much is a million kg. What could it be? Think about it. Tell me during lunch. Okay. At the end of lunch, you should tell me. Then next problem. This he showed you, HR diagram. Forget what it is. Okay. All you need to know is this is luminosity of a star with respect to the sun's luminosity. You can't read it very well. I'm sorry. This is 1, which means the sun's luminosity is here. 10, 100, 1000, 10,000, 1 million, 100,000, 1.1, 0.01, 0.001, 0.0001 times the solar luminosity. This is the temperature. This is 12,000, 10,000 Kelvin, 7,500 Kelvin, 6,000, 5,000, 4,000, 3,000. Okay. I'm taking a star here. Can you see the star in the center of the circle? And this star, they are the same temperature of 4,000 Kelvin. Correct? This luminosity is 10,000 times the solar luminosity. This star's luminosity is 0.01 times the solar luminosity. Now, what can you infer from this? Same temperature. The stars are same temperature. One of them is 10,000 times solar luminosity. The other is 100 the solar luminosity. So, what can you infer about these two stars from this, assuming it's a black body?
How large they are.
Efficiency you can assume black body, na? Black body means maximum efficiency.
Luminosity depends upon the size of the star.
Is that true?
Yeah, because here they both are on the same.
So who wants to tell me? Okay, so what is the ratio of the sizes of these stars? So tell me, you don't have to go to the board. Tell me from here. I gave you powers of 10 very easily. So what will be the ratio of the size of these two stars? Tell me. This 10 power 4, this 10 power minus 2. What's the ratio of the two luminosities? What is the ratio of luminosities? What is the value? What is the ratio of these two luminosities? 10 power 6. Luminosity goes as same temperature for both. T is same for both. R squared. This 10 power 6, then how does R go as? What is square root of 10 power 6? 10 power? 10 power? 10 power? What is version going? No. So star 1 is 1,000 times larger than star 2. That's amazing, right? I'm telling you the two stars which you can see in the night sky. One of them is 1,000 times the size of the other one. So you can imagine supposing a star is 1,000 times as large as our sun, you cannot imagine how big it is. I can't tell you imagine. You cannot imagine how big it is. Sirius B, which is 5,000 kilometers size, comes here. Sirius B is here, the one we calculated in the previous one, right? So Sirius B is 5,000 kilometers, and then this star is a factor of 100 or 1,000 more than this, and this star is another factor of 1,000 more than that, right? So all that you can tell without knowing anything. You don't have to take a spectrum, you don't have to know too much astronomy. Just black body and thermodynamics will tell you all of this, right? Now, I have a question. I will tell you, it's a fact that there are more red colored stars in our galaxy than white colored stars. Okay, it's true. Now, these are white color, blue colored stars. This is red colored stars. Because white, these are white and blue because they are hotter, red because they are cooler. Luminosity goes from 100,000 times the mass of the sun to 100,000 times the mass of the sun. Now, though there are many more red stars in the galaxy than blue stars, why is it that if I go out and see the night sky, which we'll do tonight, actually most of the stars you see are going to be white and blue and not red? From this figure, can you explain this very basic observational fact? The theoretical fact is that there are many more red stars than blue stars. Effectively, there are many more low mass stars than high mass stars. Okay. On the other hand, the many more blue stars which are visible to the naked eye, that's important, than are red stars. Now, based on this figure, this plot, can you explain why? You don't need to know any other astronomy, just this plot. This is luminosity, 100,000 to 0.0001. This is temperature from 30,000 to 3,000. And this is blue stars, this is red stars. Why are most of the visible stars blue or white, though there are many more red ones in our galaxy? Visible. The hint is visible stars. No. It's to do with this galaxy. Yeah, tell me. What do you think is going on? Right, tell me. Yeah, so exactly. So you can see that most stars are falling in this line here. Most stars are. And in this line, the blue stars are much more luminous than the red stars, right? The blue stars are a factor of 10 power 7 or 8 more luminous than the red stars. Though there are many more red stars, because the blue stars are on average brighter, we see mainly blue stars in the sky and not red stars. Exactly. So the brighter stars are blue, right? Here. And therefore you see more blue stars in the sky than red stars. Though there are many more red stars than blue stars. That is the point. Is it clear? Okay. Then we're almost at the end. Tell me when we need to stop. Okay. 2 minutes. Okay. Okay. So what kind of stars are the visible red ones? So I say most stars are blue. For it to be visible, they are very bright, right? So the stars, some stars are red, like Rohini, Aldebaran is red, Betelgeuse is Adra is red, and so on, right? Jeshta, Antares is red, and so on. So there are some red stars which are very bright, right? Now, for a red star in this temperature to be very bright, where should they be? Here or here? Here. Now forget distance. They should be luminous. They're very luminous. Then what does it tell you? They're larger. So most of the red stars you see very bright in the sky are much larger than most of the blue stars you see in the sky, because it's only the luminous red stars you see which are larger. In fact, they're called supergiants and red giant stars. Okay. So all this, so we can explain a lot of what we're seeing in the sky with our eyes just with thermodynamics, not even statistical mechanics. Okay. Should we do this or not? Okay, fine. This is Saha equation. Sorry, Saha ionization equation. Okay. Now we saw this. He showed you why the Balmer line peaks at 10,000 Kelvin rather than at 30,000 Kelvin. Now stars usually have 10% helium by number. Okay. Stars are not purely hydrogen. Roughly by number, 10% are helium nuclei compared to roughly. Okay. Now, how will this fact affect the stellar temperature at which H alpha line peaks, which is 10,000 here? This is assuming This 10,000 is assuming that the star has only hydrogen. Okay, look at the equation here. Okay, now if you add helium to it, a 10% helium extra to it, will the location temperature of this peak shift this way or remain same? Again, you just have to look at the equation and then look at this figure and try and answer the question qualitatively. So if you throw an extra helium, what changes in this equation for hydrogen? This is ionized hydrogen by neutral hydrogen. That is proton to hydrogen atom. If I throw an extra helium, which variable, which quantity here changes? No, this is still, I'm talking of hydrogen. This equation is for hydrogen. But there's some quantity here which changes because I've thrown extra helium. What is it? Can you check? Can you look at it? Yeah, I agree, it will change, but assume same temperature for this argument. Mass electron. Oi. Yeah. What is this? What is this number? What is this quantity? Ne. Electron density. If I have extra helium, some helium will be ionized. Ne will be more or less. If the extra helium which is ionized, will the electron density be increased or reduced? Increased. For the same amount of hydrogen, I have extra number of electrons, right? If I have extra number of electrons, then what will happen to Ni plus 1? What do you think will happen to the temperature at which this is peaks? If Ne increases, what will happen to the ionization number? Decrease. And therefore, it will decrease. So which of these curves? So this ionization fraction, now the green curve, it will decrease, right? So therefore, the peak will shift to left or right. It will shift to right. You need higher temperature, right? So you need hotter temperature. So the temperature at which Balmer line peaks is higher if you put in the actual composition of a star, which includes helium and so on. Because the effective number density electron density is no longer the same as the proton density. It's more because you're getting extra electrons from non-hydrogen atoms as well. Therefore, you would find out that the temperature is not 10,000, it will be slightly more. Why?
The ionization should be less.
No, we're not talking of fusion. This is all happening in the outside, the atmosphere of the sun, right? In the center of the sun, it's completely ionized, fully plasma. Ionization is 100% in the center of the sun. So you only have protons and electrons and helium nuclei, nothing else. 10 million, right? Here we're talking of 10,000, right? At 15 million Kelvin in the center of the sun, there is no ionization fraction. Ionization fraction is 100%. There is no atom cannot exist at 10 million, 15 million Kelvin, right? It's completely ionized. Helium is ionized, everything is ionized completely, right? Okay, this is clear? Again, it's qualitative argument, that's all. Okay, then, yeah, last question. Oh, yeah. Last question. Again, qualitative only. There we go. Now, he showed you Balmer lines, na? H alpha, H beta, and all that. Balmer lines we all read. Now, other atoms also have lines. Calcium also has lines. Calcium has a very famous line called H and K line in the blue. Okay, this is well, here H and K line. You see these two lines, absorption lines, a pair. Here, here, here. Here you can't see much. Here you can't see much. Between here and here, you can see the H and K pair. Two is a doublet. It's a calcium doublet. Okay. This doublet absorption line is due to singly ionized calcium, whose ionization potential energy is 6.1. For hydrogen, it is 13 point. This I should wake you up with sleep. You should tell me. Hydrogen ionization energy is how much? 13.6 eV. Ionization calcium is to become singly ionized is 6.1 eV. Okay. This singly ionized calcium has two absorption lines, so H and K. Now, for many, so it's a huge, one of the huge puzzles Meghnad Saha solved was this in his third of his 4 papers, right? People knew that the calcium absorption line was much stronger in the sun, which is around G5 here, than the H alpha line here. Okay, so calcium was much stronger. So people thought that there was more calcium in the sun than hydrogen, right? People genuinely thought for many decades that the sun had more calcium, more sodium, etc. Because the sodium lines, calcium lines were much stronger than the hydrogen line. So obviously they thought must be more of those elements in the sun. Now Saha's equation then completely overturned that. And so what the question is this, right? Before Saha, it was thought that sun had much more calcium than hydrogen. Now, knowing Saha's equation and knowing that obviously we don't have a calcium sun, it's not made of bone, right? It's a hydrogen, primarily hydrogen sun. How can you explain this discrepancy using Saha equation qualitatively? Tell me. The fact that at this temperature where the sun is, the calcium line is stronger than hydrogen line. So if obviously there's more hydrogen than calcium, using Saha equation, how would you explain that the calcium line is stronger than hydrogen? No, no, mass. That's hmm. No, no. So the line is strong. We know the line is strong. So using Saha's equation and using what he said about the Balmer line peaking at 10,000 Kelvin, Balmer line H alpha line peaks here. The sun is here. That's lower temperature than 10,000 Kelvin. Sun's temperature is lower than the peak temperature for Balmer line, but the calcium line is stronger, but it's less calcium than hydrogen. So what's going on? Look at this. Look at this. Compare that with So what's going on? So so much more calcium on the sun surface is found in a singly ionized form compared to hydrogen, most of which is neutral in the sun's atmosphere. The Balmer line peaks means is mostly ionized, let's say, right? So Balmer line peaks at 10,000 Kelvin, which means a lot of the hydrogen is ionized roughly at 10,000 Kelvin, or ionized half, let's say, around this, right? Whereas the calcium is ionized much lower temperature because ionization potential is much more. So much more calcium is ionized here, but the calcium is actually much less in number than hydrogen. So will it do the trick? That's the question, right? Answer is yes. So for a sun's temperature of 6,000 Kelvin, you can calculate using Saha equation, and I hope you do that later. 1 in 200 million hydrogen atoms only is neutral. Okay, so it's still ionized a lot, but then 1 in 200 million is neutral, and you need a neutral atom to have Balmer lines, right? So sorry, I made a slight error last. Okay, where I said previously. So only 1 in 200 million hydrogen atoms is neutral, right? And that's why you're getting Balmer lines from, and at n equal to 2, capable of H alpha absorption. But calcium, almost all the calcium is singly ionized. Okay, but the calcium to hydrogen ratio is 0.5 million. So for every for every 0.5 million hydrogen atoms, for every 500,000 hydrogen, there is one calcium. But much larger fraction of calcium is singly ionized than hydrogen, which is neutral. And 0.5 million is less than 200 million, right? So therefore, you end up with more calcium atoms being singly ionized in a state which can give you H and K absorption than the number of hydrogen neutral atoms which can give you Balmer absorption because they are n equal to 2. That is why, though calcium to hydrogen abundance is so high, is the other way around, right? Calcium to hydrogen is 1 over 0.5 million. You still get much stronger calcium absorption than hydrogen. From the Saha, just from Saha equation, and the fact that calcium ionization potential is much less than hydrogen ionization. That's all you need. So okay, still clear? Kind of. Okay, we'll stop here.